Okay, dear chairpersons, dear colleagues, ladies and gentlemen, my name is Vuk Marović. I'm studying for my master's degree at Energy and Process Engineering Department of Faculty of Technical Sciences in University of Novi Sad. Corresponding author of this paper is Assistant Professor Damir ďAKOVIĆ, and Vuk Marović, myself, is the author. As it is known to all of us, wood is used by mankind since its origin, and at first it was used as firewood and to build weapons and tools. Later, application of wood area expanded. It was used later in construction industry, for masonry, in shipbuilding, etc. Now, today wood is the primary energy source for more than 2 billion people around the globe. And in overall production of primary energy, wood is participating with over 14%. Annual estimation of wood cutting for the year of 2010 was estimated to around 4 billion cubic meters, of which 60% or 2.4 billion cubic meters was used for energy purposes to produce heat. In the Republic of Montenegro, there is over 54% of total area of the Republic of Montenegro is consisted of forest land, with 0.9 hectares per capita of woodland. The Republic of Montenegro is in 8th place in Europe by forest cover. For comparison, Slovenia has 0.6 hectares per capita of forest land, Croatia 0.47 hectares per capita, and Serbia has 0.3 hectares per capita of forest land. 81% of all forests in Montenegro are intended for wood production. Overall wood supplies in Montenegro's forests are estimated to around 72 million cubic meters, and annual wood growth is estimated to about 1.5 million cubic meters, and annual cutting is about 700,000 cubic meters. That leads us to the conclusion that there is a great accumulation of wood biomass in the Montenegrin forest. Real annual potential for wood biomass production in the Republic of Montenegro is estimated to around 1.1 million cubic meters per year. So here are some examples of wood biomass consumption in the Republic of Montenegro for the year of 2011, and we see these numbers. It was used about 740,000 cubic meters of firewood, about 80,000 cubic meters of large wood residues from industry, about 7,000 cubic meters of sawdust, etc. Now, moisture in wood is quantified by moisture content on dry basics. So it is basically a mass ratio between the moisture and the wood dry matter. So, and the wood dry basically represents the removing of the moisture from the wood. So in order for wood drying to be carried out, certain conditions must be accomplished, and those conditions for the drying air are surrounding air temperature, surrounding air relative humidity, and airflow, of course. So there are many reasons for drying wood, of course, besides that it weighs less, it's more expensive. If wood is not dried properly, it cannot be used for building high-quality finished products, and there are conditions for parasites, infestations, etc. Now, here are the examples of some products, the moisture content that is allowed, maximum moisture content that is allowed for some wood products, and we see here that for the most wood products, whether they are for energy purposes or for some other purposes, is somewhere between 5 and 20% of moisture content. Well, that depends on the product itself, of course. So, and there are several methods of, there are many methods of wood drying. Air drying here is the only method that does not require big capital investments in building constructions and purchasing equipment. But this method has many limits in its use. First of all, it cannot dry the wood below some point. And second of all, we can, in this method, air temperature, air relative humidity, and airflow cannot be controlled. So this process can take very long time. Other methods mentioned here: conventional kiln drying, solar kiln drying, heat pump kiln drying, and other unconventional drying methods all require capital investments in building constructions and purchasing equipment. So in these presentations, in this work, the emphasis was on the methods that use conventional kiln drying and heat kiln drying using kiln with heat pump. So about conventional kiln. The conventional drying kiln is basically a structure. The wood is stacked in the structure, and then heat provided by the boiler is transferred to the drying kiln, and here on this air heater, drying air is circulated over the air heater, then the hot air is circulated over the wood load, and then it's vented out of the kiln as a hot and moist air. So we see that this process, since we are exhausting the hot and moist air to the atmosphere, we see that this process is probably energy inefficient. On the other hand, this type of drying allows high quality drying, because all the relevant parameters of drying air can be controlled, and those are air temperature, air relative humidity, and airflow. And on the other hand, kiln with heat pump is somewhat similar to the conventional kiln, but here also hot air is circulated over the wood load, and then hot moist air is not vented out of the kiln, but instead it goes through the heat pump evaporator. In heat pump evaporator, the air cools down and the moisture from the wood gets condensed, and then it's flushed out of the kiln as a stream of water. So it's here, and then the heat that was taken from the air at the air pump evaporator is brought back to him on the heat pump condenser. So it is obvious that this method of drying is much more energy efficient, since we practically don't waste hot air to the atmosphere. So we made a small techno-economical analysis to compare the prices of drying with these two different methods. So we used two loads with the same board sizes, same board quantity, same initial and final moisture content, and two different wood types. The oak, the one type of hardwood, and spruce, one type of softwood. In the first step, there was determined the drying regime for both wood types. The drying regime is consisted in multiple phases, for which everyone has its determined air temperature, air relative humidity, and phase duration. So in this table there are those results. The next step was determining the mass and energy balances. So it was quite an extensive calculation, and it was not represented in detail in this presentation or in this manuscript, but if someone would like to see those calculations, I would be more than happy to share them with you. Okay, and here are some results of those calculations. We see here for spruce and oak drying, thermal power required by every phase of the drying. So we see here that spruce requires more thermal power in order for its drying process to be carried out. On this graph we see amount of heat required by a drying process for each phase, and we see here that oak requires much more heat in order for its drying to be carried out. So here is the boiler thermal power required for these two types of wood. And we see here that, as we saw before in the phases, that spruce requires greater boiler thermal power, but on the other hand, we see here that amount of heat consumed during the energy process is much bigger in the oak drying process. So, after that we made a small comparison with prices for the conventional kiln drying methods and drying method using a heat pump, and we see here that drying costs for both wood types are much lower when we are using heat pump. So we decided to make a small analysis in drying cycles to calculate the investment payback period in drying cycles in two cases. If we are to replace the existing conventional kiln with kiln that uses heat pump, and if we are choosing the new kiln, that investment payback period is going to be when we decide to purchase a new kiln with heat pump instead of new conventional kiln. So we see, of course, that that purchasing the new kiln with heat pump makes more economical sense than replacing an existing conventional kiln. Since in previous results there was shown that drying spruce took much shorter time. So in working hours we see that investment payment period for spruce drying is much shorter than for the oak drying. So to the conclusion we saw in the beginning, there is a great potential for wood biomass use in the Republic of Montenegro. We presented that whether wood is intended to be used for energy purposes or for some other purposes, it needs to be dried out to some point. Wood drying is energy demanding process, as we saw on those graphs, and choosing a heat pump over a conventional wood drying kiln could make economical sense in some cases. But I would like to point out one thing here. We have to consider that owners of the wood drying industry may have their own sources of biomass in forms of residues or waste, or may have access to wood biomass by a cheaper price. So if we take that into consideration, it is a big question whether purchasing a kiln that uses heat pump is profitable or not. So, and we also saw in this example that purchasing a kiln with heat pump is more profitable when it is intended for drying wood types similar to spruce. At least that is the conclusion of my calculation. Are there any questions? Okay, thank you for your attention.
Thank you very much.